Good day everyone. In this series, we are going to learn about the most important parameter of our planes, what, and how we are measuring it. This is of course, airspeed. As everyone has probably thought, this is the speed of the air over the surfaces of the aircraft. But things are way more complicated than that. For starters, we have 6 types of airspeed. Indicated airspeed, which is what the instrument in your cockpit is showing. Calibrated airspeed, which is what the instrument should be showing. Equivalent airspeed, which is a measurement of the dynamic pressure, expressed as an equivalent to a free-flowing mass of air that is not compressed. We'll get back to this in the future. Next, the most important one in my opinion, the true airspeed. This is the exact, true speed at which you are moving through the mass of air. If you apply the wind speed, and the correction of the larger circumference through which you are moving than that of the ground, you will get the next one. Ground speed. I don't think this needs any explanation. The last one, which is a bit more complex, is the Mach Number. This is the ratio of the true airspeed to the local speed of sound, the latter which can vary with the air temperature. Let's begin our learning with the first couple. To understand the relation between them, we'll take a look at how they are measured. This is a Pitot Tube. It features a long tube placed parallel to the aircraft's longitudinal axis, connected to a spring-loaded aneroid capsule, and one, or a few holes placed at 90 degrees to it, connected by small tubes to the outside of the aneroid capsule, itself placed inside another sealed chamber. To understand why some types of errors appear, or why some corrections need to be applied, you first need to learn that all the pneumatic instruments, in all aircraft, are calibrated using the International Standard Atmosphere. This is a mass of air that has a sea level pressure of 1013 millibars, or 29.92 inches of mercury, and a temperature of 15 degrees Celsius. As the altitude increases, the temperature will drop by 2 Kelvin, which is the same as 2 Celsius, for every 1,000 feet increase in height. The density will decrease by 1% for every 600 feet increase in altitude. DCS actually calculates this at 2% for 1,000 feet. The front of the probe will pick up incoming air and feed it to the capsule. This is called total air pressure. The outside of the probe will measure the ambient pressure of the air and feed it to the static chamber. This is called static pressure. The capsule measures the difference between them, something called dynamic pressure, and in turn, turns the needle on your airspeed indicator via a set of gears, or feeds the data to an air data computer. The airspeed indicator in your plane can be either mechanical or digital. The first one will show you indicated airspeed, while the latter will display calibrated airspeed. To understand the difference between them, we have to think about the conditions of the measurement. The aircraft does not move on rails, it shifts about in 3 axes. As a result, the speed shown to you will be subjected to errors. Air entering at an angle, or gusts of wind, thermal convections, and side slip will affect how accurate the information is. Also, the construction of the instrument itself, and that of the aneroid capsule, is not perfect. Thus, the airspeed indicator has some corrections built in, but not in all cases, as we can see with the Spitfire. For those reasons, testing is required to determine how accurate the indicator really is. At the end, a graph will be produced to show what your indicated airspeed should be in relation to what is actually shown. This is called a calibrated airspeed correction graph. So basically, calibrated airspeed is indicated airspeed, corrected for position, and instrument errors. Now that you have some understanding of the first 2, let's learn about the next one, equivalent airspeed. As you start picking up speed at higher altitude, you may notice that your indicated speed is higher than it should be, and that the center of lift is moving further out. This is noticeable when the plane requires more and more nose-up trim as your speed gets higher. This is because the air hitting the pitot probe, and at the leading edge of the wing, will get compressed, and the stagnation point in front of the wing will get closer to it. For this reason, the air over the top of the wing will follow a slightly different path. This will change how the plane reacts to changes in angle of attack. When pulling high loads at high speeds, the wing will stall violently at speeds that it should not. This is called a high-speed stall. To sum it all up, the incoming flow of air will behave like it has a lower speed. That's why this is called equivalent airspeed. Now, we've come to our most important speed, the one that's a direct indication of the kinetic energy of our planes, true airspeed. If we take the E, A, S, and apply a correction of 1% for every 500 feet of altitude, and 2% every 10 degrees Celsius, that means correcting it for density, we get our true airspeed. If we take as an example the standard for DCS missions, 20 degrees, which means a plus 5 degree ISA deviation, with a standard barometric pressure, at 20,000 feet we have 40% increase in T, A, S from altitude, and 1% from the temperature, resulting a 41% increase. We will assume a compressibility correction of 96%, as this would vary with many factors. At 250 knots of calibrated airspeed, times 0.96 equals 240 E. A/S times 1.41 equals 338 knots of true airspeed. If we take a look at DCS, in the same conditions, the true speed is 343 knots. Pretty close. The difference is due to the higher compressibility factor taken into account by the sim. So, we have indicated, it becomes calibrated by correcting for instrument and position errors, equivalent if we also correct for compressibility, and true, by applying the density corrections. At last, we have arrived, the Mach number. There are two numbers of interest to us here, true airspeed and the local speed of sound. LSS, as it's abbreviated, is dependent on the air temperature. That means that as you climb higher, the speed of sound will be lower. This will also be compounded by the temperature at sea level. A lower temperature will result in the same Mach number at a lower TAS. In this comparison at 35,000 feet, you will notice that the true speed at Mach 1.4 is different for different temperatures. In this demonstration, you will notice that at 880 knots at sea level, which is higher than we used to have at 35,000 feet, the Mach number is lower than at high altitude, even if the sea level temperature is lower. This concludes our airspeed tutorial. I hope you will find this helpful, and stay tuned for more lessons. If you have any questions, place them in the comments section below and don't forget to like or dislike.